Hey y'all, welcome back to Alakazam Math Made Easy. I wanted to go over the first actual theorem, formal, complex worded theorem in Calc 1, and that's the intermediate value theorem. Hopefully, I remember when I was taking Calculus 1 the first time, the fact that it was called a theorem kind of threw me off a little bit and made me think it was super complicated, unapproachable. Hopefully this video kind of breaks it down a little bit in a way that can hopefully make it understandable and help you see why it's useful. So yeah, we'll jump right into it. So intermediate value theorem states that for any continuous function between x equals a and x equals b, so any continuous function between two x values, the function will intersect the line y equals 0 at least once where the function exists between those values, right? So the first thing we're going to break down is it has to be a continuous function, which means that it's not going to jump, skip, there's no holes in it, there's, no surprises really. The second part is that we're only looking between two x values. So let's break down this first example. We're looking between x equals a and x equals b. So that means that between these 2 points, I have to be able to draw a straight line, right? And I'm looking also between two y values. That's what this piece says. It's really complicated. It's kind of an ugly way of writing it, but that's all they're saying is that they're looking between two x values, which they tell you here, and they're looking between two y values, which they tell you here. So we're looking between a, f of a, b, and f of b, which means I'm essentially looking inside, I'm not going to use blue, I'm looking inside this box here. Right, so I'm only considering that chunk of the function. So I've established the area I'm looking. What they're saying is if I pick some w, some value w that exists between f equals a, or f of a and f of b, so between my two y values, the function has to cross that value. There has to be a point somewhere between that value, or between those y values, that equals w. Right? So basically all they're saying is if I were to draw any horizontal line, right, between f of a and f of b, the function will cross it at least one point, right? And as you can see, the lines I just drew, that's true. The function crosses at least once at every horizontal line inside that box. So let's look a couple of the little minor details in what that breaks down to, right? So it says at least once, which means I can look at a complex function like this inside that same box, right? Inside my f of a, f of b, a and b box, right? And I can draw all the horizontal lines I want, and the function will cross it at least once, but that at least once means that it can happen more than once, right? So that's what's demonstrated in this function. You can tell that if I draw the line at w, it actually crosses the function 3 times. So that's an interesting feature about this, is that it specifies that it can cross definitely more than once, but it has to cross at least once. So the application of this, the reason why this is such a cool theory, is that you can use this theory to find the zeros of a function, right? So I'm looking at this one now between f of a, f of b, b, and a, right? And I drew my w at 0, right? So my w right here being on the x-axis means that it's 0. And as long as I have some f of a that's less than 0 and some f of b that's greater than 0, it has to be the case that my function will cross the x-axis if it's continuous. So that's actually the most common application of the intermediate value theorem, is that it is a way to approximate where that 0 is, right? So what I'm going to do is I'm going to run through examples, but I'm also going to run through a kind of interesting use of it, right? So how useful is it to know that between two x values, there's a 0, right? If I gave you some wide range like 3 and -5, in a real world application, that might be worlds away. That's like saying, is there water between, California and Europe, right? So that might be a huge broad window. But you'll see in a minute, once I break down, you can actually kind of adjust those windows to a reasonable range, a range that works best for you. And you can find values that get closer and closer and closer to that 0. So I kind of spoiled it a little bit, but we'll jump into it. So the first example is we're looking at that wide window, right? So I'm saying I'm looking between x equals 1 and x equals 5, and I'm evaluating this function. So first of all, step 1 is I have to find my FA and FB. So here's my A is 1, B is 5, right? So I have to find my f of A and f of B. I find that by plugging in my values into the function I'm given. So if I plug in 1, I get -2 times 1 plus 5 is 3, right? Boom. So that's my f of A. And then I plug in 5, and I get -2 times 5 is -10 plus 5 is -5, and I get my f of B. So first of all, the thing to notice is that one of my numbers is negative and one of my numbers is positive. And the question was asking, is there a 0? So because, first of all, because this is a linear function, right? It's a linear, like literally straight line. It has to, by definition, be continuous. There's no way to draw a straight line without picking up, picking up your pen, right? So that's not possible. So it has to be continuous. So there's that. We've satisfied that condition. We've also satisfied the positive and negative, and I'm looking for a 0. So 0 lies in that window, which means that yes, there will be a 0 between these two x values. So that's that answer. But like I said, that might not be super helpful, right? So that might be, like I said, like saying, is there water between California and Europe, right? We know there is, but it doesn't help us to know that it's a window that big. So the question is, how can we narrow that range down to be more helpful, right? So we're going to start by testing other numbers, right? So let's try x equals 2. If I plug in x equals 2, and I want to see, because if I'm approaching this, if I know f of 1 is positive, right? I'm going to try to find a number near f of 1 that's slightly less positive, right? So this trend is going down because as I increase my x value, my y values are decreasing. So we know that as I increase x, my y value should decrease. So picking a value for x higher than 1 should give me a value closer to 0 than 3. So let's try 2. So if I plug in 2 to that same function up here, I get -2 times 2 is -4 plus 5 is 1. And it's still greater than 0, so I can use that. Boom, that's helpful. Let me try another number, right? So I want to try a number near 5. And I want to test to see if it's still negative. So let me pick 4. That's the most logical number to test, is the next one down. So I'm going to test it and then compare it. So if I plug in 4 to that function, I get -2 times 4 is -8 plus 5 is not -1. -2 times 4 is -8 plus 5 is -3. So that's still negative. I can use that, but let's try to narrow it down a little bit, right? So, oh, I see what I did. I forgot to draw the next lesson, or the next the point. So if I were to test x equals 3, right? If I plug that in, -2 times 3 is -6 plus 5 is -1. So if I plug in f of 3, it's still less than 0, but that ends up being -1. So what I'm saying is, I guess that's a good demonstration, right? If I chose x equals 4, technically my window is still valid, but it's still wider than it could have been. Whereas if I pick x equals 3, it demonstrates that the window can get narrower and still tell me that there's a 0. So that's the point, I guess, that I was trying to make, is that now I know that while yes, there is a 0 between x equals 1 and x equals 5, I actually know that that 0 lies between x equals 2 and x equals 3. So again, because the example was linear, it was super simple, right? Like it was a straight line, we know it's continuous, blah, blah, blah. We could have also solved that. We could have solved for that 0 by setting that function equal to 0 and just solving for x. We could have found exactly where that 0 is. But for some values in real life that are super like modeled by super complex equations, like my background is in biomedical engineering, right? The equations that govern the system in your body are nowhere close to linear. So all of those super complex equations, you can't necessarily find the 0 by just setting it equal to 0. So intermediate value theorem can help you approximate zeros and evaluate little chunks of the function at a time to help you find where those zeros might be and then govern it that way. So that's the application of intermediate value theorem. I know it doesn't seem like it's something that might be super applicable in the immediate, but once you get down into classes further in your major, like there's applications for business majors, there's applications, because think about it from a stock market point of view. If you're trying to find when the value of the stock will equal some value, that's not a linear relationship. The behavior of like price versus for a certain stock is not a linear relationship. So you can try to approximate it by modeling it out into the future and then using intermediate value theorem to not help you find zeros, but help you find where it'll equal that value of W. So intermediate value theorem is a super exciting thing, even though it sounds kind of boring and abstract right now, but it'll be used further down the line to kind of justify why we're doing derivatives and stuff. So if you learned something from this video, feel free to like it. If you want to keep up to date with the stuff that I'm posting, subscribe to my channel. And if you press the bell, it'll notify you when I upload things. But other than that, that's all I've got. So good luck.